You all, Barely Berry Jr. back for some more classical dynamics. Uh, Ironically, the early parts of relativity, we review some classical dynamics. So I'll be reviewing some classical dynamics concepts, particularly gravitational potential. So this will currently lead to the next thing that we will start. Today was our first day in relativity class, so I'll put this under classical dynamics, and specifically the concept is classical dynamics, but it's still leading into relativity, so keep that in mind. Understanding is that all of the um, concepts of classical dynamics can be derived from relativity, even though it takes like uh, easier just to go straight to classical. So let me share my screen here, and we have so looking at chapter 5 of the textbook, Classical Dynamics, Thornton and Marion. And anybody who shows, be sure to let me know if there's any issue with the audio. So we're going to go through this step by step. So we start with what they call equation 5.1, Newton's law of universal gravitation. F equals negative G M M over R squared. And it's a vector force. And 5.3 these references are to classical dynamics. So we have gravitational field vector. If I recall, this is similar to the electric field in electrodynamics, or electrostatics, I guess I should say. G equals F divided by the small mass. That equals negative G M over R squared R hat. And to get the gravitational potential, we have equation 5.5, which says that the gravitational field vector, which is similar to the electric field, and to be sure what I mean, if you go to Coulomb, F equals K Q1 Q over square F, and the electric field equals K Q over squared R hat, which equals F over Q1. Stop K on this one. So G is related in a similar way. So I think that's quite interesting. So for 5.5, the gravitational field vector is the same thing as the negative gradient of the gravitational potential, what is what you want. So easy enough then. Thinking we could just take an integral to get phi. Let's see how that works out. So basically, if I do g equal integral of both, should give the gravitational potential. So the integral of g equals the integral of g m over r squared. And I still this r hat. I don't recall what we do with. Oh, well, potential is doesn't have a direction. I have to think about that. Over r to be integral of g m integral of r to the negative 2 dr. That is going to be negative g m r to the negative 1 divided by negative 1 plus the constant of integration. So that'll be g m over r c. I've noticed that the textbook, oh, negative, what the textbook has, I'm not sure exactly what we do with the constant of integration or the r hat, but I'll just not worry about that for now since it's not needed. Side. So that's that. So this is our gravitational potential. So if we were to get the gravitational potential of sun at the sun's surface, so we need to get some sun facts. So this site here, the sun fact sheet, one of my favorite sites. I seem to use it in almost every class. Use it in astronomy, use it in physics. So let me position it real fast. Right, so this is the NASA sun fact sheet. There's some good stuff in there. And we want to calculate this for the sun's surface. So we need R and we need M. So I at R equals R, well not but star equals negative G M of the sun over R of the sun. So that's going to be G equals Wonder if you did you ever have that memorized? So I'll see what page it's on in Thornton and Marion. It was 6 point something. Let me click online. I know it's everywhere. So I'm going to the Britannica site. G equals 6.6743 10 to the negative 11 meters cubed over kilograms second squared. We have that. From our sun fact sheet, we have that the mass of the sun is 1,988, excuse me, 1,988,400 times 10 to the 24 kilograms. And we have the radius of the sun, which I've calculated before, but I'll use the official value. There we go, right here. Volumetric mean radius, 695,700. Be sure to drop a line, by the way. When I calculated this, I'll let you know what I found it to be while that's loading. Right, so let's go back to the pad. It says loaded. Let's see what value I got. So looks like when I calculated the diameter, I got, oh, I had it in miles, so it'll make it difficult. But it was pretty close to the official. The diameter for the official is uh 865,000 miles, and I had 860,000 miles. But I'm not going to go through the process of calculating that to kilometers. So let's keep going. So we have this, and all we have to do is plug it in. So gravitational potential, sun at the radius of the sun equals 6.6743 10 to the negative 11 meters cubed over kilograms second squared over 695,700 kilometers. That's going to be also times 1,988,400 times 10 to 24 kilograms. Put this in, see what it equals. I'll see if there's some way to. I know there's a. I can plug up the calculator and download, but maybe I can plug it up and show it as well. But probably won't do that. I don't like continuously unplugging and plugging stuff to my computer. So here, by the way, I'll put 10 to the 3 for the kilometers. So 695,700 10 to the 3. So that's in meters. We have 10 to the 24 there. That's in kilograms. And 10 to the negative 11. That gave me an error. So I'll tell. I forgot to put a multiplication. Mm, Two multiplication again. So that time I got 1 times 10 to the 11. And let's see what the units are. So I remember to put my 10 to the negative 11 here. Put my 10 to the 24 here. It's already in kilograms. And 10 to the 3 here to make that in meters. So when I cancel these kilograms and cancel this meter, that gives me meter squared over second squared. That can't be right. Maybe I put my gravitational constant units wrong. Let me see. Second squared meters cubed. Yep, that's the units. Hmm. Squared over second squared. So let me check this and see what may be incorrect. EM over R. This up. Units. Gravitational potential. Like I'm missing I think that's kilograms squared in the denominator now. The thing about that, the units seem like they should be joules. Why am I missing a kilograms? I'll just ask Professor about that tomorrow. See what I did incorrectly. And for the time being, we can get the potential of the sun at the Earth. We can say I equals AU, which equals, I believe this is already in the uh, sun fact sheet. On AU, Earth, distance from the Earth, minimum maximum mean. We have 149.6 times 10 to the 6 kilometers. Uh, Everything should be the same as before, except let's call this RE, or capital E for Earth. So I not, well, I, the sun at RE equals, I'll just copy this down, radius will be this. So let's change that one thing. The mass of the still doing the potential of the mass of of the sun, so the mass is the same, G is the same. See what we get just changing that one thing. Mm, 49.6 10 to the 6, and that's kilometers. So I'm still putting another 10 to the 3 here for that. So that's times 10 to the 3. Becomes 8.87 10 to the 8. I'll just keep it what it is for now until I figure out what the discrepancy is. Maybe I'll look one more time and see if I can see what it is. The equation seems to be right. Gravitational potential is Gm over R. See if they, yep, that's what it is. Chanukah is missing a kilogram squared. Looks like. Oh no, they just use different units. So hold up. First time Britannica let me down. What they're doing. So let's back up and look at this. These units. And I see the units the book has. So we can parse out and make these the same. So basically, if I multiply this by kilograms over kilograms, it becomes uh, we have kilograms meter squared over second squared, which is joule. Kilograms meter squared over second squared. And that leaves meters over kilograms squared. Distance meters cancel. Not precisely what the book has, but let me put it in book form. So joules is kilograms meter squared over second squared. Actually, newtons is kilograms meters over second squared. So this is newtons times meters squared over kilogram squared. And this is the units that the book has. So if I put the first one in, the meters cancels, 1 kilograms cancels, then I get joules per kilogram. Put the second one in, I have 1 meter on top, 1 meter, 1 kilogram on the bottom. So it's Newton meters over kilogram. Newtons is kilograms meters over second squared, and joules is kilograms meters squared over second squared. So those are the same. Yet one of the sites I see is saying that potential gravitational potential should be in joules. So again, I'll just see what professor says tomorrow. But got a little bit worked out. So it's always the bane of my existence. Hold up. Show it again. So this here is basically the dimensional analysis of the proper units from textbook, which I guess technically all the units from the Britannica. Look at it tomorrow. Yeah. Let's see what we have here. And that this will give us 8.87 e to the 8 joules over kilograms for that one. will be joules over kilograms equal nu- meters over kilograms for this one. That's for the sun at Earth's surface. And I'll do one more before I close up, or maybe two more. Let's plug these in. The gravitational potential for Earth at Earth's surface. Now we have the potential of Earth, our Earth. So that equals, again, we can copy the same thing down, except now we have to change two things. So now the radius is going to be the radius of Earth. And I can go to the same fact sheet. Well, not the same fact sheet, but the same website from NASA. And there's an Earth fact sheet, which I've also used a lot. Right? So 6,000 something. But, I'll just put just right here. I'll just put 6360, 6360. Hold on. And erase that too. So of the Earth, that's 5.97 E24 kilograms. See what this is? Changing two things. 597. 5.97. Let me remember to switch back to my pad. Up to the 24. And 6360. Still putting my 10 to the 3. Make it in meters. Uh, 6.26. 10 to the 7. And now I'll just put joules per. All right, so that's that. So we did some gravitational potential problems, and I wanted to do these today so I can actually go tomorrow and ask Professor about them. So we have office hours in the morning. So what I'll probably do is find out what the difficulty with the units is, or maybe one of the sites is inaccurate or something. And I might come back later this week and mention it briefly. Thank y'all for joining. I saw a few pop in. I'll see y'all a few about tomorrow, another day this week, and keep learning.